Hello and welcome to a new video in a course on calculus. I figured that before we transition to the new chapter on infinite series and power series, that we wrap up this chapter by some more exercises on limits in order to improve your understanding of the two very important tools we introduced for the calculation of limits, namely squeeze theorem and L'Hopital's rule. So let us go over this and solve some examples. So let me remind you, first of all, that L'Hopital's rule states that if you're interested in the limit of a rational function, like it's a function over a function, where the limit of f of x and the limit of g of x, as x goes to c, like it exists, and it is equal to 0, or they're both equal to infinity. In other words, if you find the limit of f of x over g of x as x goes to some c, and it has the form 0 over 0 or infinity over infinity, then you have this property. So you can find the limit of the rational function by finding the limit of the derivative of f over the derivative of g. So let us solve some examples real quick and see why this is important. So we start with this basic example that we probably might have seen before. So we start by taking the limit of sine of x over x. This is a very important example. So if you just try to plugging in the value of x equals 0 here, you see that this is sine of 0 over 0, which is 0 over 0, and it has the form that you're looking for. And what this says thus is that this limit is equal to the derivative of the thing above, which is cosine of x in this case, over the derivative of the thing below that, which is x, so that's 1. And then you take a limit as x goes to 0, and notice here that the denominator is not 0 as x goes to 0, so that is legit, and this is equal to cosine 0 over 1, which is just 1. So this is a very important limit. This is a very important limit to keep in mind, and it's simply a simple application of L'Hopital's rule. Alright, so let's go to the second example. Okay, so so I advise you as we go through these examples to put a piece of paper next to you and write down the tricks that are appearing when we're calculating these, right? They're mainly, in this case, like they're mainly like, we're just mainly taking derivatives. There is nothing deep. But in case you think there's something that you might forget, just write it down. So let's look at this example. We're interested in the limit as x goes to infinity of e to the x over x squared. If you remember, this is called the exponential function, right? And here's one thing that I want you to remember. Exponential increase or decrease is quote-unquote fast. So what do we mean by that? What I mean here is that if you look at such a limit and you see an exponential in the numerator and a polynomial, like for example in this case x squared, in the denominator, you should expect that the limit of the exponential will beat the limit of the polynomial. So it's faster, and you should expect in this case that this limit is infinity, because the exponential is faster, it goes faster to infinity, right? So how would we prove this? We prove this by L'Hopital's rule. To see this, first of all, we know that the limit of e of x over x squared, if we evaluate, this has the form e to the infinity, which is infinity, over infinity squared, which is infinity. And thus we can apply L'Hopital's rule, and if we apply L'Hopital's rule, this will be the limit of the derivative of the numerator, which remains e of x, over the derivative of denominator, which is 2x as x goes to infinity, and thus this is again has the form, if you evaluate now, so if you evaluate, this also has the form infinity over infinity, because it's e to the infinity over infinity, and thus you can apply L'Hopital's rule again, and what do you get? You get the derivative of the numerator over the derivative of the denominator, which is, it remains e of x over 2 in this case. And now you take, you plug things back, and you get, this is infinity over 2, which is infinity, namely plus infinity. So mainly I should mention here, suggestion or trick number 1, don't give up if the application of L'Hopital's rule didn't work from the first time. In other words, for example here, we applied L'Hopital's rule once, and we got this, but this still has the form infinity over infinity. We don't give up, we try again. We try applying L'Hopital's rule to this new thing that we got. And when we do that, we see that we have this thing, and thus when we take the limit, it's going to be infinity. Alright, so we have two things here to remember. The exponential is fast, and don't give up trying L'Hopital's rule. Okay, so the next thing, or the next example we're going to go over, it's this limit, and it mainly has the same flavor as other limits. It's except that when you evaluate, you get trigonometric functions. So for this limit, I'm gonna leave it for you because it's simply the same as the previous one. There isn't much here, except that we'll be applying L'Hopital's rule 3 times. And why is that? Well, if you see here, we have x cubed here, so we want to get rid of this x cubed, and the way to do that is by we differentiate it its degree times. So the degree of this is 3, so we differentiate this thing 3 times to get what we want. So we apply L'Hopital's rule 3 times, and we use the fact that tan of x prime is secant squared x, which is 1 over cosine squared x. And once we use that, we will need also the product rule. So this is going to be u prime v plus v plus uv prime. So these are important things to remember. So the next example we want to try is this limit. It's also an important limit to keep in mind because it kind of shows up when calculating harder limits. And the trick we're going to use here also shows up when calculating different limits, so it's important to go over this. So the first thing here, so we're interested in this limit, x log of x, and if we try evaluating this, I remind you one of the properties of logarithm is that as x goes to 0 plus, the logarithm goes to negative infinity. So so it's important here to see that this has the form 0 times negative infinity, and thus we cannot directly apply L'Hopital's rule because it doesn't have the form 0 over 0 or infinity over infinity. And I remind you, the logarithm, it takes only positive values. Like, you can't evaluate the logarithm at a negative number. This is not okay. So this justifies why we're approaching 0 from from the right in this case. So so we're interested, so we're gonna so we want to send x to 0 but from the positive side. So if you remember, so if this is the x-axis, we want to send x to 0 from this side, right? So this is the positive part and this is the negative part. Anyways, so how can we turn this into something where we can apply L'Hopital's rule to? Because remember, the only tools we've learned so far are squeeze theorem and L'Hopital's rule. And squeeze theorem doesn't seem to be very helpful here. Or at least it's not immediate. So what we're gonna do is that we're gonna use L'Hopital's rule by doing a little modification to this problem. Namely, we're gonna write x ln x as the limit of ln x over 1 over x, because when we divide by it in the denominator, it's the same as multiplying by it. And this trick, so this is an important trick. I just want to write it here. So this is an important trick. Write functions of the form 1 over x ln x as ln x over 1 over x. Right, so this is an important trick when we're interested in the limit as x goes to 0. So let me just go over this. Let me write things down. It would be better. So we agreed the limit we're interested in is the same as this limit. And the first thing to try is to quote-unquote plug x in its value, and this is going to be infinity, namely negative infinity, over 1 over 0, which is infinity, and thus this has the desired form, and we can apply L'Hopital's rule to it. And if we apply L'Hopital's rule to it, what do we get? This is the same as the limit as x goes to 0 plus of the derivative over the derivative, and in this case it's going to be 1 over x over the derivative of 1 over x is 1 minus 1 over x squared, and we multiply things out. We multiply these and we get this is the limit of x squared over x, which is the same as, let me just write it here, it's the limit of negative x, which is 0. And here's a cleaner solution. You apply L'Hopital's rule to this rational function, and you get this form, and then you rearrange things and you get negative x, and what's the limit of this? It's actually 0. Okay, so this is an important limit to keep in mind, that the limit of x ln x is 0, right? So here's one way of thinking about this. Though ln x goes to infinity as x goes to 0 plus, x goes faster to 0, right? X goes faster to 0, hence it beats the ln x, and thus the limit must be 0. So here's another note. Let me just call it. So let me say it this way. Ln x is slower than x, and I should mention here that we mentioned before that x is slower than ex, right? So if we want to like arrange these from the faster to the slower, so we can write these as such. So it's ex x ln x. So this is the faster, and this is the slower. In what sense? Like, for example, in this sense, right? If we look at this, x goes faster to 0 than ln x goes to infinity, and thus the limit must be 0. So these are important when you want to get an idea of what the limit might be. But when proving things, you have to write things down, okay? So so let us go ahead and see another example. So this is yet another example that uses trigonometric functions, And I'm gonna leave it to you as an exercise. You can look at this. It's just simply the same thing. You start by derivating this because it has the form 0 over 0, and you get this thing, but that's not enough. So you go ahead and derive that again, and what you do, you get this thing, and once you do that, this is probably a typo here. Cosine of 0 is 1, so this is 1 over 6. 1 over 6. Okay, so I'm gonna leave it for you as an exercise, and here's the solution. So try this and then look at the solution and compare your answers with the solution. So let us continue now. Let's take another example, which is this thing. And here comes the important thing that I told you, which is about the rate of these functions. So we have the exponential, we have x, and then we have ln x. So the above thing is faster, and as we go down, it becomes slower. So if you look at this, you see that we have x e negative x, which is x over ex, right? So this is as x goes to infinity, okay? So you see ex goes to infinity as x goes to infinity, and x also goes to infinity as x goes to infinity. However, ex goes faster, right? And since ex goes faster, it's gonna beat this, and it's gonna make it 0. So let's see why is that true. So this is the motivation, and let's prove it. So the limit of x over ex as x goes to infinity, this is what? This is infinity over infinity, or takes this form. And thus, the limit by L'Hopital's rule is going to be the derivative of the numerator, which is 1, over the derivative of e of x, which is ex, which is actually 1 over infinity, which is 0. Right? So just as we expected, the limit of this thing is 0 because ex is faster than x. Okay? So this is also an important limit to keep in mind. And as an exercise, I'm gonna leave this limit for you to practice the idea of what we just said. You just apply L'Hopital's rule multiple times, and you get the limit that you have. And there's something important here to see, which is that if you look at this thing, you see that if we kind of separate the fractions, if we write this as ex over x cubed minus 1 over x cubed minus 1 over x squared minus x squared over 2, so this is x over x cubed over x cubed. If we write this as such, it's not clear what the limit is, right? So the other important trick is that when you have like a fraction that's separated, try bringing things back together, because it might be the case that bringing things back together might actually give you a limit, might actually give you a value. Unlike here, for example, the evaluation at 0, it's kind of telling you that there's some sort of 0, there's some sort of infinity here, negative infinity here, and it's not clear. So the other trick here, it's important. Usually when you have the form infinity minus infinity, try taking common denominator and combining fractions. Right. So this is an important trick for you. So if I've asked you to find this limit, you might have suffered actually doing that, because you see here, evaluating this, it gives you infinity, and evaluating this, it gives you infinity. So you have the form infinity minus infinity, and like it's not clear for you what you can do, because it's not like you can't apply L'Hopital's rule directly, and you can't apply squeeze theorem. So when you get this form, try combining the fractions because it might help you to find the limit, just as in this case. All right, so now let's go to applications of squeeze theorem. So let's see here. So squeeze theorem, it states that if you have a function g and you're interested in the limit of g, and you can put g, quote unquote, put g between two functions. In other words, you can put g between h of x and f of x, and suppose also that the limit of f of x and the limit of g of x exists, then and it's equal to the same L, then the limit of g of x must be the same. In other words, if this goes to L and this goes to L, then this must also go to L. Alright, so let us take two examples or so on the application of squeeze theorem. So the first one we're gonna try is this thing. So we want the limit of x squared cosine of 1 over x, right? So the issue here is that cosine, the limit of cosine as x goes to infinity is not defined. So if you see here, this is, if you evaluate x, this is going to be cosine of 1 over 0, which cosine of infinity. It's not really defined. So we need to get rid of this cosine because it's annoying and we cannot just get rid of it directly. So what is one way of getting rid of cosine? And this is a trick that I need you to remember. Usually when you have cosine and sine, the trick is that the sine of x and the cosine of x, these satisfy the inequality that they're less than or equal to 1. In other words, sine x is between 1 and -1, and cosine x is between 1 and -1. So this is always true for real x, and so you can use that to get rid of this ugly cosine, and you can apply squeeze theorem afterwards. So let us see how. Well, x squared cosine 1 over x is bounded by x squared, because this is bounded by 1, right? And this is lower bounded by minus x squared, because this is lower bounded by -1. And notice here that it's important that this x squared is actually non-negative. So this right hand side, it goes to 0 as x goes to 0, and this also goes to 0 as x goes to 0, and thus by squeeze theorem the limit of this thing is actually 0, right? So, and you can actually look at a cleaner solution here. So you use this inequalities or these inequalities, and you get this, and you use squeeze theorem to get that this limit is 0. Alright, so let us do another example. So let us do this example because it's also an important one. So usually when you have a limit as x goes to infinity and you have a sine and cosine function, you should be careful here because the limit of these functions is not defined at infinity. So you should figure out how to get rid of these. You want the limit of this, and you can't, like, by evaluation it doesn't work. So we've seen that before, that the limit of sine x over x as x goes to 0, this is actually 1, right? This is something that we've seen. So we ask the question, what happens if we add cosine in the numerator? And what happens is that the limit will be 0. So let us see why. So let us do it over here. So I'm gonna introduce a new trick for you, which is called the absolute value trick. Like, instead of applying squeeze theorem by two inequalities, you look at the absolute value of the function that you have, which is in this case this thing, and you use something called triangular inequality. So remember, triangular inequality says a plus b in absolute value is less than or equal to a in absolute value plus b in absolute value. And this is important for you to remember. So this is a new trick that I want you to remember. If you have two things in absolute value, they're going to be less than the sum of the absolute values. Sine x plus cosine x. But wait a second, the biggest this can be is 1, and the biggest this can be is 1, right? Because these functions are bounded between -1 and 1, and thus in absolute value, this is the biggest it can be is 1 for sine and 1 for cosine, and this is bounded by this thing. So this is what we have. On the other hand, what we have is that this is lower bounded by 0, because the absolute value of anything is non-negative, right? So we have two inequalities now. We have 0 this side, and we have this function this side. Now 0 goes to 0 as x goes to infinity, because it's a constant function. And this is just 2 over absolute value of x. And what happens as x goes to infinity is that this is going also to 0, right? As x goes to infinity, because 2 over infinity. And thus by squeeze theorem, this inside is going to what? To 0 as x goes to infinity. And since the absolute value goes to 0, it must be that the function itself goes to 0. And thus this proves the limit. Another way to do this is to use these two inequalities, these two over here, and thus you have that the sum of these is between 2 and -2, because you add these two, you add these two inequalities, and thus you have this inequality for your function that you're interested in. And once you notice that this goes to 0 and this goes to 0, you can apply squeeze theorem, and you get that this limit is actually 0. So in the next video, we'll be discussing infinite series, and it's going to be a new chapter that we'll be moving to.